Hello everyone, welcome all of you to this channel. See, this is the application of number of stereoisomers. We have studied how many stereoisomers can be there. So when we do it in calculation, what type of question can come? For that reason, this is the first concept. That is formula for how many stereoisomers a chiral compound can form based on number of chiral center. We know that the carbon is chiral because it is attached to four different groups. So if in a molecule more than one chiral center is present, then if n is the number of chiral center or asymmetric center, then the number of stereoisomers it can produce is 2 to the power of n. So this is the actual calculated, expected how many stereoisomers can be present. But if there is any internal symmetry in the structure of that molecule, generally we use the Fischer projection to see the Fischer structure to see. If there is any internal symmetry and if there due to this, if there exists any mesoform, then the number of stereoisomer is bound to reduce. So each new chiral center will double the possible stereoisomers in general. If we are not talking about meso compound. If there is one center, 2 to the power of 1, 2, 2 center, 2 to the power of 2, 4, 3 center, 2 to the power of 3, 8, 4 center, 2 to the power of 4, 16. So this is in general. So like this, I have given 4 questions along with the concepts. Let us see one by one. Question number 1. A compound has two chiral center. There are two chiral center. N is equal to 2. Because of an internal plane of symmetry, that means there is an internal plane of symmetry, one of the stereoisomer becomes a meso compound. That means you get a meso compound. For that, obviously, the number of stereoisomers should decrease. How many stereoisomers are possible? There is only one meso compound. So for this, the calculation becomes little bit easier. Why? Because if there is only one meso, what will happen? The maximum number of stereoisomers possible is 2 to the power of n. N is the number of chiral center. Here the number of chiral center is 2. So 2 to the power of 2, total stereoisomers can be 4. But there is one mesoform. So due to this mesoform, two configuration becomes identical. Regarding mesoform, we have discussed in other videos. So two configuration becomes identical. Now what will happen? Normally this would give rise to 4 stereoisomers. So these 4 stereoisomers are what? They are RR, SS, RS and SR. What is this RR, SS? See, this is the configuration around the chiral centers. And regarding this arrangement also we have discussed in the other video in order of their priority. Okay, so in order of priority, in order of the atomic number of the atoms or groups that are arranged around the central around the chiral center. So like this we can say there are two chiral centers, so it can be RR, SS, RS or SR configuration. These are the 4 stereoisomers that can generally be present. However, if the molecule is having a plane of symmetry, then what special happens? The configuration RS, SR are actually mirror images. But because the molecule has internal symmetry, mirror image can be superimposed on itself, because internally within the molecule, within the structure of the molecule, there is a plane of symmetry that actually divides the molecule into two identical parts. So the mirror image can be superimposed on itself. So in that case, the RS structure and the SR structure, they give the same structure. The RS type of stereo representation and SR, they will give the same structure. They will give the same compound. So this structure is the meso compound. The same compound that you will get out of RS and SR, you get one compound Now this compound is the meso compound because both are identical. You are considering it to be one structure. So this is meso structure, meso compound. The other two is RR and SS. So what you got? RR. SS is the obviously the enantiomer of RR. And RS and SR, they are identical. So they are the mesoforms. Total you got 3 stereoisomers. Example is tartaric acid, the simplest example everyone will give you, because we need to understand with simple examples. Tartaric acid has this type of structure which I have shown you. Now RR and SS are optically inactive, optically active enantiomers. RS kya hai? It's meso. So it's optically inactive. Why it is optically inactive? Because it has an internal symmetry factor, which is the plane of symmetry. So this is the structure which you can see. This is tartaric acid structure. First one you can see tartaric acid, where two chiral centers, the two carbons, they are the chiral centers. One COH up and down, and left hand side H and H, right hand side OH and OH. So this is a tartaric acid. You can see there is a plane of symmetry, and so one part I have shown by red, the other part is obviously identical to it. But this is the mesoform. Why it is the mesoform we are saying? Because you know that the mesoform, one part which I have given by black, I have marked that part. This is actually the mirror image of the other part. Okay, so this part is the mirror image of the other part. That is RS. If one is R, the other is S. So it is the mirror image. Okay, so RS and SR both are same structures, because within it you can see the structure is such that one part is the mirror image of the other. Why? Because lateral inversion occurs now. So the one which is shown in the left hand side in the mirror image will be in the right hand side, and the nomenclature where you are seeing the right hand side OH is there, in its mirror image it will be on the left hand side. So they are the mirror images, and so this is meso. Now over here we can see these two are enantiomers, and so they are optically active forms. Mesotartaric acid is internally symmetric and so optically inactive. That is an important point. Now here the upper and the lower halves we can see are mirror images. Just now we have discussed. There is an internal plane of symmetry. Therefore it is a meso compound and optically inactive. So to understand this, I have given you an example from your daily life observation. You have seen butterfly. The left wing and the right wing, they actually see, they are identical, right? Now, when the left wing and the right wing is folded along its body, along its center line, then this body, we can assume the center line, we can assume to be the plane of symmetry, because both the sides, the wings are symmetrical. And along the plane of symmetry, if the butterfly folds the wing, then both the wings will actually coincide, they match exactly. So the mirror image is the same molecule. If I consider the mirror image of the left wing is the right and the right is the left, then they are the same molecule. That is why two configurations, they collapse into one mesoform, because they are the same configuration. If the two mirror images, they coincide, they overlap. So question 2 is, a molecule contains 3 chiral center as per the formula 2 to the power of 3. So based on the formula there can be 8 stereoisomers, right? Now, but one internal plane of symmetry, so there is leading to mesoform. So what is the maximum and possible number of stereoisomers? So here we can see, because the symmetry is there, so some configuration will be identical. Actual stereoisomers will come up to be 6, because one meso is there, so you get 2 such forms. So 8 minus 2, you will get 6. But if you go the normal way, we can see, if the molecule has an internal plane of symmetry, then some stereoisomer becomes optically inactive, they are the mesoforms, and the two configurations may represent the same compound. In that case, the two structure it coincides into one, right? So the number of total number reduces. So final number of stereoisomers will be 6, which includes the two meso stereoisomers which are optically inactive. Okay, the 4 optically active stereoisomers which are there forming 2 pairs of enantiomer. So that is 4 plus 2, which you are getting 6. Question 3. Consider a compound with 2 chiral centers arranged symmetrically such that RS and SR structures are identical. How many stereoisomers can exist? 2 chiral center are there, so 2 to the power of 2, 4. But there is one identical form, that is RS and SR. They are identical, so they will give one structure. So 4 minus 1, I'll get 3. So possible configurations are RR, SS, RS and SR will be same. They will give identical structure. They are the mesoforms due to the presence of internal symmetry. It is arranged symmetrically said. So total stereoisomers will be 3. Let us see question number 4. Here we can see a compound contains 4 chiral center. So as per normal calculation, 2 to the power of 4 जो कि 16 होना चाहिए, so 16. But the molecule has complete internal symmetry. Now when it is not one symmetry, internal symmetry, it is complete internal symmetry. Obviously more than one forms will be there. Also producing 2 mesoforms. So it is declared you have 2 mesoform. So find the number of stereoisomers. So as per the formula it should be 16. But due to internal symmetry, some stereoisomers will overlap and so the structure stereoisomers becomes 10. How it becomes 10? Let us see. Where overlapping takes place. RS and SR overlap. So here 4 are there. So if 4 are there, we can consider RSSR configuration. This will overlap with the SRRS configuration. So now what happens? This becomes mesoform. They will become mesoform because they are the mirror images. One part is mirror image of the other. See, R has the mirror image as S. And in both the cases, the plane of symmetry will be between, that means just after the 2 carbon atom or between carbon number 2 and 3. So in the Fisher representation. So this reduces the total number. So instead of 16, you are getting what? The 4 pairs of enantiomers. From there you are getting 8 stereoisomers. 4 pair of enantiomer. From there you are getting the 8 stereoisomers. And here you are seeing 2 meso compounds. So 8 plus 2, total 10 stereoisomers are possible due to the mesoforms within the due to the internal symmetry and the 2 mesoforms that it produces.